Hello everyone, hope you are doing very well. So, today we are going to see the NCRT exercise questions of our chapter Coordination Compounds. So, let's begin our today's topic NCRT chapter 5 Coordination Compounds. And today we are going to do NCRT exercise questions number 5.4, 5.5, 5.6, 5.19, 5.28 and 5.30. These are the questions that majorly carries the important concepts covering in this chapter. So this is disclaimer. The objective of today's lecture. So after attending this lecture, you will be able to understand the reactivity of coordination complexes. Okay. The topics that are going to be covered according to the NCRT. First of all, the labile coordination complexes we are going to see. Then non-labile coordination complexes. Then beta, or you can say overall formation constant. And then we will see the NCRT exercise questions one by one. Okay. So let's begin. So first of all, let's begin with the first topic, that is labile coordination complexes. Labile coordination complexes are characterized by their fast reaction rates in ligand substitution processes. So the process that include the ligand substitution, where ligand is adding or subtracting, okay, it is substituting into the complex. In those process, the labile coordination complexes are characterized by their fast reaction rates. So labile coordination complexes, that means the coordination complexes that are reactive. That means they are going to have fast reaction rates. Their reaction rate is faster in the ligand substitution processes. The key points. So first of all, the rapid ligand exchange. Rapid means fast ligand exchange. So ligands are quickly and easily replaced by other ligands in the surrounding solution. So when this ligand substitution process happening, when our labile coordination complexes is participating or forming, then the reaction rate is faster, and it is including rapid ligand exchange, where ligands are quickly and easily replaced by the another ligand in its surrounding solution. Fast reaction rates. So the substitution reactions occurred very rapidly, and they often completed within seconds or minutes at room temperature. Okay, so these reactions which are happening, like ligand substitution reactions, whose reaction rate is faster, so their reaction rate is very faster, that the reaction occur so rapidly, often within seconds or minutes, even at room temperature. That means without providing any external conditions. Low activation energy. So as the reaction rate is faster, so activation energy of these processes will be lower, right? So energy barrier for the ligand exchange process mechanism is relatively low, allowing reactions to proceed quickly. That means faster reaction rates. Okay, so they are like interrelated, that for these ligand substitution processes, the fast rate of the reaction will be there. Why? Because the ligands are very quickly replaced by the other ligands which are present in the surrounding solutions, and due to which the reaction rate will be faster. Often the reaction is completed within seconds or minutes at room temperature, and the due to which the activation energy will be lower. That means this energy barrier for the ligand exchange is very lower, or you can say relatively lower, to allow the reaction to proceed quicker or faster, okay, to have the reaction rate as faster. Examples of the electronic configurations. If we talk about the octahedral configurations, so in the octahedral complexes, the D0 configuration, for example, which is present in Ti4 positive, titanium 4 positive. So D0 configuration for example, which is present in Ti, titanium 4 positive. So titanium is having the normal configuration as argon 3d2 4s2, but when it is donated, its 2 electron become 4 positive, its electronic configuration of the d orbital will become 0. And the d1 and the d2 octahedral complexes, high spin octahedral complexes, which includes the configuration of d4, d5, d6 and d7. General factors contributing to the lability of the coordination complexes. So lower charge on the central metal ion. So if the charge on the central metal ion, the coordination complex or coordination entity, if the charge on the central metal ion will be lower, that means if its oxidation state will be lower, there will be a larger lability of the coordination complexes. Okay, so this is a factor which is contributing towards the lability of coordination complexes. Similarly, larger size of the central metal ion. As the size of the central metal ion present in the complex will be larger, the lability will be larger. The reactivity of the coordination complex will be larger. Presence of electrons in anti-bonding EG orbitals, which weakens the metal ligand bond. Also, if there is any presence of electrons in the anti-bonding EG orbitals, it is also a factor which is contributing to lability, and it is also weakening the metal ligand bond, which is increasing the reactivity of the ligands or ligand exchange process rate, right? So ligand this due to this weak metal ligand bond, ligand can easily exchange with the another ligand present in the surrounding solution, and this reaction rate of ligand exchange will be faster, right? So these are the factors that are contributing to the lability of the coordination complex. If we talk about inert coordination complexes, inert means non reactive. Okay, so inert coordination complexes are defined by their slow reaction rates in the ligand substitution processes. So in the ligand substitution process, if you want to identify the inert coordination complexes, those complexes will have slow reaction rates. Okay, their reaction rate is very slow. They slow the reaction, they show the reaction very slowly. Okay, those type of coordination complexes that will be present in the ligand substitution process are inert coordination complexes. Their key points: slow ligand exchange. So they involve slow ligand exchange. That means in the ligand substitution process, ligands are not easily replaced, and the substitution reactions proceed very slowly or not at all under the typical conditions. So even under the typical conditions, the ligands will not exchange, or it will exchange very slowly, or the reaction will proceed very slowly. Okay, it is not easily replaced. So you have to provide some critical conditions for this ligand substitution process in the case of inert coordination complexes. Second key point is that slow reaction rate. So they include the reaction rate very slow. So reactions can take minutes, hours, or even days to reach the equilibrium. So even reaction to proceed, it can take minutes, hours, or even days. So their reaction rate is very slow. High activation energy, and due to the reaction rate or slow reaction rate, their activation energy is very high. Significant energy barrier that must be overcome for ligand substitution to occur. So there is significant energy barrier that is available that must be overcome for any ligand substitution to happen or to occur in the case of inert coordination complexes. The examples of the electronic configuration in the octahedral complexes: it includes the D3 configuration, which is actually, for example, present in chromium 3 positive. So chromium have configuration argon 3d5 4s1, and when it loses its 3 electron from 1 from 4s and 2 from 3d5, it will get 3d3 configuration, right? Low spin d4, d5 and d6 configuration, which is, for example, present in low spin cobalt 3 positive complexes and low spin iron 2 positive complexes. Cobalt 3 positive means cobalt configuration is argon 3d7 4s2. After donating its 3 electrons, it will have 3d6 configuration, which is also low spin. Low spin because in the presence of strong field ligand. Okay, and the low spin iron 2 positive, that means the iron is having argon 3d6 4s2. When it releases its 2 electron, it will gain 3d6 configuration. Low spin 3d6, strong field ligands is present in it. Okay, forming low spin complexes. D8 configuration, which is present in the square planar geometry complexes, like the platinum 2 positive, they are notably inert. Okay, so platinum 2 positive, if it forms like platinum 2 positive, it forms as a like if the platinum 2 positive will be present as a central metal ion in the square planar complex, it will be notably inert because it will show the D8 configuration. The general factors that are contributing to the inertness, first is higher charge on the central metal. So when you can identify that this coordination complex will going to be inert, okay, so what are the factors that are contributing towards the inertness of the coordination complex? The first is higher charge on the central metal ion. As the central metal ion is going to have the higher charge, it is the coordination complex formed by that central metal ion will be inert coordination complex, or you can say inertness will be increased. Similarly, small size of central metal ion. If the size of this central metal ion is smaller, it will contribute to the inertness of coordination complexes. And the last is high crystal field stabilization energy, that is CFSE, which strengthens the metal ligand bonds and increases the activation energy for the substitution. Okay, so if the value of CFSE is larger, that means the bond between the metal and the ligand is also going to be stronger, right? And this is going to increase the activation energy for any kind of substitution. So substitution will be slower or not easy. Okay, and this metal ligand bond is it is a bond which formed between the metal and the ligand, which is a metal coordinate bond. Okay, so due to the high crystal field stabilization energy value, the metal ligand bond will get stronger, strengthens, and due to which the activation energy will be increased for any kind of substitution of ligands. So these are the factors that are contributing towards the inertness of the coordination complexes. Let's now talk about the beta n, or overall formation constant. What is it? Let's understand by the definition. So, overall formation constant, that is beta n, is the equilibrium constant for overall reaction of a metal ion, that is M, combining with n number of ligands, that is L, to form a coordination complex. Okay, coordination complex like MLN, where L is representing the ligand, which is N in number, N is representing the metal ion in a complex. Okay, and this beta N, which is a overall formation constant, is our equilibrium constant for all the steps, including in the overall reaction of metal ion with the N number of ligands one by one to form the coordination complex MLN. It measures the thermodynamic stability of the complex in the solution. A higher beta n value indicates more stable complex. So if the overall formation constant is higher, if its value is higher, it is saying that a stable complex or a more stable complex is going to be formed. Relationship with stepwise formation constant. So stepwise formation constant like K1, K2, K3 up to Kn. Okay, for each step there is a stepwise formation constant. And what is the relationship of overall formation constant with these stepwise formation constant? That is, we are going to see. Step 1 includes the reaction of the metal and the ligand. So metal plus ligand giving us Ml complex. So it is having a stepwise constant K1. This reaction is having a stepwise constant K1 because this is the first step. And if you want to write the K1 value, that is the constant, formation constant value, it will be product upon reactant. Product is Ml complex divided by, the reactants are M and L. So M concentration multiplied by L concentration. These square brackets are denoting the concentration of products and the reactants differently. Okay, so the K1 value, that is the formation constant of first step, is this. Second step will be the addition of one more ligands to the formed complex in the previous step. So we have Ml complex formed. So Ml will add up one more L into it, one more ligand into it, and form a new complex Ml2. So the ligand number will increase. Okay, and this reaction or this step is having a stepwise constant K2. K2 value will be similarly find out product upon reactant. Product is our Ml2 complex divided by the concentration of Ml reactant and the L ligand reactant, right, which is acting here as reactant. So product upon reactant. Okay, now as you know the constant rule, if you are for equilibrium constant or for formation constant, like here, if you are writing its value in the form of product upon reactants, here in the power there is also the stoichiometric coefficient that will come according to the reaction, right? But here in the reaction every stoichiometric coefficient is 1, so in the power of product and the reactants there is 1 present. Okay, now for the final complex, that is MLN, because the final you are getting or you are adding the number of ligands is n number of ligands, right? So you are finally forming a complex MLN where n number of ligands are present. So for that complex, the overall formation constant, that is beta n, is product of all the individual stepwise formation constants up to the n ligands. Okay, so what I said, that as you all know that for the each reaction we just have written the stepwise constant value, right? Now K1, K2, K3, K4 up to Kn, there will be different values of K as per the reactions, as per the steps, right? If you want to add them together to get the final value of K, or you can say final value of overall formation constant, that is going to be the product of all Ks, K1 dot K2 dot K3 dot K4 up to Kn, right? So this is the rule, right? That when you are adding the reactions, you have to multiply their constants, right? So for the overall formation constant, that is beta n, this will going to be equals to the product of all the individual stepwise formation constants up to the n ligands. Up to n ligands, the steps you have followed and the value of constant you have derived, you just have to multiply them, and the product of all those individual stepwise formation constant will be equals to the overall formation constant, that is beta n. So beta n will be equals to K1 multiplied by K2 multiplied by K3 up to the Kn product, right? Let's see the equilibrium expression. General reaction. So for the overall formation of a complex MLN, if you want to form the overall complex MLN, you have to write this overall reaction for this formation of a complex MLN, where L is representing the ligands and N is representing that n number of ligands is present in our complex. So for this, the general reaction is M to the power X positive. That means M has charge, let's say X positive, and it is adding with n number of ligands and forming this complex MLN whole X positive. This is the complex that we are getting. And for this general reaction, for the overall formation of complex MLN, the overall formation constant or beta n will be equals to, similarly, product upon reactant. Product is our MLN, so MLN to the power X positive, right? And divided by reactant. So the reactant is Mx positive, so Mx positive and the other reactant is L, ligand. So L to the power N, because N is a stoichiometric coefficient present here, so it will go in the power of the reactant in this relation between the overall formation constant and the concentration of product and the reactants. Okay, so this is the value of overall formation constant that we have just derived by using or by writing this overall formation reaction of this complex MLN. Now here the MLN X positive is equilibrium concentration of our complex. Mx positive is equilibrium concentration of free metal ion, and L is the equilibrium concentration of free and neutral ligand. Instability constant or dissociation constant, that means Kd, that means dissociation constant, or K inst, that means instability constant. What are these? So basically the reciprocal of overall formation constant are dissociation constant or instability constant. It represents the equilibrium constant for dissociation of the complex back into its metal ion and the ligand. Okay, so dissociation means you are dissociating the complex now, and it like the dissociation constant will represent the equilibrium constant for the dissociation of our complex that we just get into back into its metal ion and the ligands. So you can write the Kd, that is dissociation constant value, is equals to the reciprocal of overall formation constant, that is beta n. Higher overall formation constant means lower dissociation constant value, that indicate the greater stability, because we are proceeding towards the formation of complex. Okay, that means we have higher beta n value, that means we have lesser dissociation constant, because they are inversely related. So it is if there is higher beta n and lower Kd, this is indicating a greater stability of our complex. Factors that affects stability and this the beta n for any complex. First of all is nature of metal ion. Higher the charge density, so if there is a small size and higher charge of the metal ion, it leads to stronger metal ligand bonds and thus higher beta n. Okay, so if our metal ion is having higher charge density and smaller size, that will leads to the stronger metal ligand bond which is forming between the metal and ligand, and thus it is stabilizing our complex, and thus overall stabilization factor, that is this beta n, this will increase or this will be higher. Electronic configuration, second factor is, so high crystal field stabilization energy often correlates with higher stability. If you are having higher value of CFSE, that means you have higher stability of your complex, so that is also a factor that is contributing to the stability of the complex or beta n. Next is nature of ligand. Now metal ions we have just seen. Now how the ligand nature will affect the stability. So first is basicity of ligand. If we have the more basic ligand, that means it will act as better electron donors to donate the electrons to metal. Metal will act as strong electron acceptor, and thus we will get a stable complex by this relationship, right? So if you have more basic ligand, that will act as better donor electron donor, that will form stronger bond between the metal and ligand, and you will get a stable complex. Chelate effect, this you all know that chelating ligands or the effect they create, that is chelate effect, this forms significantly stable complexes than comparable monodentate ligands. So if you compare with the monodentate ligand having only one donor atom which can attach with the metal ion, if you are taking a chelating ligand that can create a chelating effect in the complex, that is going to be significantly increase the stability of the complex. Presence of pi bonding. So ligands that are capable of pi back bonding, for example, carbonyl and the cyanide, they form exceptionally stable complexes. Okay. So let's begin our exercise quotients. First is 5.4. The question is what is meant by unidentate, diadentate, and ambidentate ligands. Give two examples for each. So you have given some time, try to analyze this question, and then we will see the answer. Okay, let's see. So the ligands may contain one or more unshared pair of electrons, which are called donor sites of ligand. Right? This you all know that ligand can have one or more than one unshared pair of electrons that they can donate to the metal, and those unshared pair of electrons are called donor sites of ligands. Depending upon these number of donor sites, ligands can be classified as follows. First is unidentate ligands. They are the ligands. Uni means one. Dentate any denticity. So unidentate ligands are the ligands with only one donor sites available, and they are called as unidentate ligands. Okay, they have only one donor site, so they can like only one donor atom can attach to the uh, metal ion in the complex. Okay, those are called unidentate ligands. For example, ammonia and chloride, etc. So in the ammonia, nitrogen have lone pairs, and it is only one site or one donor site that is available, that is going to be like contribute in the bonding formation with the central metal ion. Similarly, in the chloride, we have negative charge on the chlorine, and this is going to uh, form the bond. The chlorine is going to form the bond with the metal ion with these number of charges. Okay, so only one donor atom or one donor site is available, so these ligands are unidentate ligands. Next is diadentate ligands. They are the ligands that have two donor sites. Dia means two, so they have two donor sites and they are called diadentate ligands. For example, we have NH2, CH2, CH2, NH2, where you can see two nitrogens are present. Its name is ethane 1,2 diamine. We have two nitrogen, and at both the nitrogen we have lone pair, that is our two donor sites that is available for making the bond with the central metal, with the central metal ion in the complex, right? So this ligand is having two donor sites, so this is a diadentate ligand, ethane 1,2 diamine. Similarly, the example CO negative, CO negative, where there is O negative and O negative. So we have two donor sites available that can donate the electrons to the metal d orbitals and form the bond with the metal in the complex. So this is also a diadentate ligand. Name is oxalate ion. Next is ambidentate ligands. What are these? Ligands that can attach themselves to the central metal atom through two different atoms. They are called ambidentate ligands. So a ligand, if it is having two different atoms, okay, that have this ability to attach with the central metal atom, they are called ambidentate ligands. For example, nitro and nitrito. Nitro means in this N double bond single bond O, nitrogen is available for the attaching or binding with the central metal atom in the complex to form the complex. Whereas in the nitrito, this oxygen is available for the bonding with the central metal atom to attach themselves to the central metal atom in the complex. Okay, so this is the example of ambidentate ligands, that within a same ligand, two different atoms, nitrogen and oxygens, are present for the attachment to the central metal atom. So they are ambidentate ligands. Here in this, as I said, the donor atom is nitrogen, and in this nitrito, the donor atom is oxygen. Let's see the next exercise question number 5.5. Question is, specify the oxidation numbers of the metals in the following coordination entities. So you have to tell the oxidation number of metals in these complexes. First is cobalt H2O cyanide En whole twice whole 2 positive. Then cobalt Br2 En whole twice whole positive. Then third is platinum Cl4 whole 2 negative. Fourth is K3FeCN whole 6. Fifth is chromium NH3 whole thrice Cl3. You have given some time. Try to solve this question and then we will see the answer. Let's see. The first coordination entity, where let the oxidation state or let the oxidation number of cobalt that you have to find, let it is X. So cobalt is having X, plus water is a neutral ligand, so 0, plus cyanide is an anionic ligand having negative charge, so -1, plus En, ethylene diamine, is a neutral ligand, so 2 times 0. This is equals to +2, which is the overall charge present on the entity. So when you solve for X, X minus 1 equals to +2 and X will be equals to +3. So the cobalt will be having oxidation number +3. For the second entity, cobalt bromine whole twice, En whole twice whole positive. Let's say again the same process for the cobalt. Let's say oxidation number is X. So X plus 2 times -1, because there are two bromine and bromine have negative charge. So 2 times -1 plus En charge is 0. So 2 times 0 equals to the overall charge, that is +1. Solve for X. X minus 2 equals to +1. -2 goes here on the right hand side. So X become +3. So here also the cobalt charge or oxidation number is +3. For the third entity, platinum Cl4 whole 2 negative, platinum is having, let's say, X plus 4 times -1, chlorine is an anionic ligand, is equals to total charge, that is -2. So this -4 will go in the right hand side and X will be +2, because +4 minus 2 will be +2. So platinum charge or oxidation number will be +2. Similarly, in the fourth entity, K3 potassium iron cyanide whole 6, we have iron as X oxidation number, plus cyanide has it is an ionic ligand, so 6 times -1 is equals to overall charge, that is -3. 6 times -1 is -6. When you take it here in the right hand side, it become positive, so X become +3. That means the iron is having here +3 oxidation state. Lastly, the fifth entity, that is chromium NH3 whole thrice Cl3, we have X for chromium, plus ammonia is a neutral ligand, so plus 3 times 0, plus chlorine is an anionic ligand having negative charge, so plus 3 times -1 equals to the overall charge of the complex, which is 0. So X minus 3 equals to 0, that means X equals to +3. That means charge or the oxidation number of chromium here is +3. So this is how you can calculate the oxidation number for the metal ion present in each of these given coordination entities. Let's see our next question, question number 5.19. The question is, chromium NH3 hole 6 hole 3 positive is paramagnetic, while nickel CN hole 4 hole 2 negative is a diamagnetic. Explain why. You have given some time. Try to solve this and then we will see the correct answer. Let's see. So this is the representation of the electronic configuration present in the chromium. So for chromium atom, the atomic number of chromium is 24, for which the configuration is 3d5 4s1. Okay. So you can see we have 5 single pair electrons present in the 3d orbital and 1 electron is present in the 4s orbital. Now, chromium having here plus 3 oxidation state because ammonia is a neutral ligand. So, the overall charge present on the complex will become the oxidation state of chromium. So, chromium 3 positive means 3 electron will be lost by it. So, 1 is from the 4s and 2 is from the 3d. So, the remaining 3 electrons will be available in the 3d and 4s become empty. 4p is also empty. Right. Now for this complex formation, chromium ammonia hole 6, we have 6 number of ligand. This is an octahedral, you can say this is an octahedral complex. Okay. So chromium NH3 hole 6 hole 3 positive formation, we are needing 6 different orbitals for the electron donation from the each ammonia ligand to form the bond with the chromium metal ion, right? And because ammonia is a weak field ligand according to the spectrochemical series, it doesn't cause any pairing of unpaired electrons present. So these three unpaired electrons remain unpaired as it is, and then you will take two available 3d orbitals, one 4s and three 4p orbitals for the electron donation from the ammonia ligand, approaching ammonia ligand towards the chromium to form the bond, to form the complex. Okay, and you will get D2 because 2 orbital from D you have taken, S because 1 S, and P3 3 p orbitals you have taken in the hybridization. So you will get D2 sp3 hybridization, and each of the orbital will get the electron pair donated from the each ammonia ligand, or you can say 6 ammonia ligand that are going to approach or that are going to form the bond with the chromium metal. So for this complex chromium ammonia hole 6 3 positive, charge on the ammonia is 0. So the charge on overall complex is plus 3. So the oxidation number of chromium will become plus 3. And the configuration of chromium 3 positive is D3. We have a weak field ligand, ammonia, present here. So the pairing of 3d electrons happen? No, it does not happen. So hybridization will be D2 sp3. That means uh, the 2d orbitals, 1 s orbital and 3p orbitals will going to be contribute to the hybridization. Okay. Unpaired electrons, yes, there is unpaired electron presence in the 3d, right? Because of D3 configuration, D3 means 3 singly unpaired electrons. So these remain unpaired due to the presence of weak field ligand ammonia. So these are remaining unpaired. So we have a presence of unpaired electron, right? So it will cause the magnetic nature of this complex as paramagnetic. Now, if we talk about our another complex, that is nickel cyanide hole 4 hole 2 negative, where the central metal ion is nickel and nickel atomic number is 28. That means 3d8 4s2, right? 3d8 4s2. 8 electrons in the 3d orbital gets filled where you are getting two unpaired electrons, all other are paired, and in the 4s you get one paired electrons. Okay, so 3d8 4s2 4p will remain empty. Now here in this complex, the nickel coordination the nickel oxidation number is +2. Why? Because cyanide is an anionic ligand, it will carry -1 charge. So nickel x plus 4 times -1 equals to -2. So nickel will be +4 -2, that is +2. So nickel will be having +2 oxidation number. +2 means it will donate its 2 electron, which is from outermost 4s orbital. So you will get this configuration of 3d8 4s0 4p0, right? Now you are seeing that here we have cyanide ligand, which is a strong field ligand, right? And 4 number of ligands are approaching towards nickel. So we are needing 4 empty d orbitals of the nickel metal atom, right? So for that, first of all, cyanide is a strong field ligand, so it will cause the pairing of unpaired electron. We have only 2 unpaired electron in the nickel 2 positive, so they will paired up and we get one empty 3d orbital for the electron donation of cyanide ligand. So we get 1d, 1s and 2p orbitals hybridization, in which each orbital will be filled by the electron which is donating by 4 cyanide ligands approaching towards the nickel to form the complex. Okay, so for this complex, nickel Cn whole 4 whole 2 negative, the charge on the cyanide is -1 because it is an anionic ligand. The charge on complex is -2. Oxidation state of nickel here is +2 if you calculate, and the configuration of nickel +2 is d8 if you talk about the d orbital, d8 and the 4s2 also. And because the cyanide ligand is a strong field ligand, so pairing of 3d electrons will happen. Okay, so in the nickel 2 positive we have d8 configuration after the donation of 2 electrons. Now due to the presence of strong field ligand, that is cyanide ligands, these pairing of 3d electrons will happen. Yes, it will happen, and the 2 unpaired electrons will undergo the pairing up, and the hybridization you will get after it is dsp2 after you obtain one empty 3d orbital. So unpaired electrons present here? No, it is not, because all the orbitals are paired up, and the remaining empty orbitals will also get occupied by the electron donated by the each cyanide ligand to form the complex with the nickel, right? So unpaired electrons present? No, it is not present in the 3d orbital. So the character or the magnetic character of this complex will be diamagnetic. Okay, so this is the reason. This is how stepwise you can explain that why this chromium complex is paramagnetic while nickel complex is diamagnetic. Let's see our question 5.28. Okay, this question is saying that how many ions are produced from the complex cobalt NH3 whole 6 Cl2 in the solution. So you have to tell that from this complex in the solution how many ions you will get when you dissolve it in the solution. 6, 4, 3 or 2. So you got some time, try to solve this and then we will see the correct answer. Okay, let's see. So the complex cobalt NH3 whole 6 Cl2, when it dissociates, it will dissociate into the following ions. In the cobalt NH3 whole 6 2 positive, and it will we will get 2 chloride negative. Okay, because Cl2, that means 2 chlorine are present outside of this coordination sphere or coordination entity. That means 2 chloride ions are counter ions. So you will get 2 different chloride ions when you dissociate this complex, and this coordination entity will remain intact. The reaction it will follow, cobalt NH3 whole 6 Cl2. It will dissociate into cobalt NH3 whole 6 2 positive plus 2 chloride negative. The number of ions that are producing here is 2 chlorine ions and one of this cationic ion, that is CONH3 whole 6 whole 2 positive. So this cationic complex you are getting as ion 1 plus 2 these chlorines. So there are total number of 3 ions that is producing after the dissociation. One complex cation, that is cobalt NH3 whole 6 whole 2 positive, and the another one is counter anion that you are getting chloride negative, which is 2 in number, right? So the total number of ions produced is 3. Let's see our next question, question number 5.30. Question says that amongst the following, the most stable complex is. So you have given the complexes, you have to find out the stable complex. Iron H2O whole 6 whole 3 positive, iron NH3 whole 6 whole 3 positive, iron C2O4 whole thrice whole 3 negative, or iron Cl6 whole 3 negative. From these complexes, you have to identify the most stable one. You have given some time. Try to solve this and then we will see the answer. Okay, let's see. So we have the correct answer as option third, which is iron C2O4 whole thrice whole 3 negative, whose structure is something like this, where iron is the central metal ion and it is surrounded by 3 oxalate ions, which is C2O4 whole thrice, 3 oxalate ions, CO, C double bond O, C double bond O, and O negative, O negative. Okay, so COO negative, COO negative. Here also, here also. So we have 3 ring-like, or you can say chelate ligands, that is oxalate ligands, that are surrounded this iron, which is a central metal ion, and this whole complex is having a 3 negative charge. Why it is more stable? The stability of a complex increases by chelation. Okay, so if there is a chelate ligand present in our complex, which is showing the chelate effect, that will automatically going to increase the stability of complex. So oxalate ion, that is C2O4 whole 2 negative, is a chelating ligand which is having a density of 2. That means it can bind through 2 oxygen atoms, 2 donor atoms with the central metal ion. And oxalate ligand form rings around this metal atom. So it will increase the stability of the complex by this chelate effect shown by the oxalate ion. And most stable complex therefore will be iron C2O4 whole thrice whole 3 negative. Okay. Okay. Thank you so much. That's all for today's chemistry session. Thank you.